It was a 3-foot stick. That's the first thing men said when they picked one up. 3 feet long, maybe a little more. Shorter than a man's arm span. Curved in a shape that looked almost awkward, recurved back at the tips. The whole thing bending away from you when unstrung, like it was trying to escape. George Frederick Ruxton, the British adventurer who traveled through the Rocky Mountain fur trade country in the 1840s, picked up a bow like this and spent several paragraphs in his journals trying to explain why he couldn't quite believe what it was. The weapon he described was old, well used. The wood at the grip was worn smooth in a way that speaks of 10,000 draws, maybe more. The sinew on the back had yellowed and gone hard, and Ruxton pulled the string to full draw, felt the resistance build under his fingers, and wrote that it was the single most powerful short bow he had ever handled. He had no explanation for that. Most people who think about Native American bows picture something roughly like a bent willow branch, a flexible stick, something a boy could carve in an afternoon. And when they think about those bows aging, sitting in a lodge for years, they assume the same thing that happens to every bent stick: it softens. It follows the string. The wood takes a set toward the curve and stays there, losing power with every season. That assumption is completely wrong. Hold that thought. The Rocky Mountain fur trade lasted about 20 years. Call it 1822 to 1840, though the edges are blurry. William Henry Ashley's famous newspaper advertisement in the Missouri Republican, March 1822, called for 100 enterprising young men to ascend the Missouri River. The men who answered that call: Jim Bridger, Jedediah Smith, Tom Fitzpatrick. The Sublette brothers would spend the next 2 decades in territory that most of their contemporaries couldn't place on a map. The rendezvous system, which Ashley invented after the Arikara killed 14 of his men on the Missouri in 1823, pulled trappers out of the dangerous river country and into the mountains. Supply caravans packed overland, mule by mule, to prearranged gathering points, primarily the Green River Valley in present-day Wyoming. The first rendezvous was July 1825 at Henry's Fork. By the mid-1830s, these gatherings drew 400 or 500 trappers, plus thousands of Crow, Shoshone, Flathead, Nez Perce, and Bannock. Men who had spent 11 months alone in the mountains emerged blinking into what looked, for a few weeks, like a small city made of hide. These men were not tourists observing native culture from a polite distance. Jim Bridger married women from both the Flathead and Shoshone tribes. James Beckworth, born in Virginia, the son of an enslaved woman and a white plantation owner, became a chief among the Crow in the early 1820s, and by his own account, practiced extensively with the bow. Kit Carson's first wife was an Arapaho woman named Wa-Nee-Bay. The mountain men who lasted, the ones who came back year after year, were men who learned things. And one of the things they eventually learned was that the bow they had spent their first seasons dismissing as primitive was, in terms of raw mechanical performance, a more sophisticated weapon than the rifle on their shoulder. That realization didn't happen quickly. It happened the way most genuine learning happens, through evidence that couldn't be argued with, delivered at close range, whether they asked for it or not. Here is what most people picture when they imagine a bow: a single piece of wood, bent. The back, the side facing away from the archer, stretches when drawn. The belly, the side facing the archer, compresses. One material does both jobs. A bow is a bending beam, and in a bending beam, the back takes tension and the belly takes compression. That description is accurate, and it contains the problem. Wood handles tension reasonably well. Pull a wooden plank and it'll stretch maybe 1% before it begins to fail. But put that same plank in compression, push the ends toward each other, and the wood cells on the compressed face buckle permanently at roughly half that strain. They don't spring back. They stay crushed. Bowyers call it set. The bow bends toward the string and doesn't fully return. Draw weight drops. The bow loses the arc it was built to hold. Every simple wooden bow, no matter how carefully made, no matter what wood you use, follows the string over time. It's not a question of quality. It's what wood does when you ask one material to handle 2 opposing mechanical demands at the same time. The Comanche knew this. The Shoshone knew this. The Crow, the Blackfoot, the Mandan, they all knew this. Not in those words, but in the practical sense that matters. They knew what happened to a bow that wasn't made correctly, and they made them correctly. Here is where the analogy most people reach for breaks down, and the break itself is worth examining. The intuitive model says, sinew makes a bow stronger the way steel cable reinforces concrete. You add a strong material to make the whole structure stronger. That's not wrong, exactly, but it misses the mechanism entirely. Dried sinew harvested from the backstrap or leg tendons of bison, elk, or deer is a remarkable material. Its tensile strength runs around 28,000 pounds per square inch. It can stretch 5 to 7% before it begins to fail. Wood, for comparison, tears apart under tension at roughly 1%. So sinew is far better at handling the tension on a bow's back than wood is. But here is where the standard analogy fails. Sinew's elastic modulus, its stiffness, is actually lower than wood's. It's not adding rigidity. What it's doing is something more interesting than that. When sinew fibers are separated into individual strands, soaked in warm hide glue made from boiled animal tissue, and laid along the bow's back in layers, sometimes 2 layers, sometimes 5, depending on the craftsman and the intended use, something happens as they dry that changes the bow's geometry entirely. Sinew contracts powerfully. As the moisture leaves and the collagen fibers shorten, they pull. They pull the unstrung bow backward into a curve that faces away from the archer. Bowyers call this reflex. A heavily sinewed bow, held unstrung, may curve so far back that the tips nearly touch behind the grip. That backward curve is not cosmetic. It is a preloaded spring. Before the archer strings the bow, the sinew is already under tension. The wood is already under compression. When the bow is drawn, the sinew handles the tension load, the job for which it is vastly better suited than wood, and the wood handles compression at reduced strain levels, well inside its failure zone. The critical result: the belly's wood never reaches the compression threshold where set begins. But there's more. Because the sinew is always pulling the bow toward reflex, it actively counteracts whatever minor compression set the belly does accumulate over years of use. The bow doesn't just resist aging, it fights back against aging. Reginald Laubin, who studied Native American archery for decades in the mid-20th century, documented that well-made sinew-backed bows sometimes gained reflex over the years as the sinew continued to contract through repeated wet and dry cycles. Some of those bows, examined after decades of use, pulled harder than they had when new. This is what the trappers were holding, a pre-stressed composite structure that stored energy not only by bending, but by the materials themselves working against each other in a carefully balanced mechanical opposition. The Shoshone bands that Osborne Russell encountered in the Yellowstone backcountry around 1835 carried the most refined version of this technology. Russell was a Maine man, 20 years old when he first came west, and his journal, eventually published as Journal of a Trapper, is one of the most detailed and honest accounts of daily life in the mountains that survives from this period. The band he found in Yellowstone were the mountain Shoshone, known to other tribes and eventually to anthropologists as the Tukadika, the sheep-eaters. They had almost nothing of European manufacture. Russell listed their trade goods: 1 old butcher knife, worn nearly to the spine, and 2 old fusées trade guns whose locks had long since failed for want of spare parts and powder. By the accounting of the fur trade world, they were desperately poor. Their bows were extraordinary. Russell wrote that the weapons were beautifully crafted from sheep horn, buffalo horn, and elk horn, secured with deer and elk sinew, ornamented with porcupine quills, and generally about 3 feet long. He was looking at the same composite principle applied to its hardest to make, highest performing variant. Horn, specifically the curved boss horn of bighorn sheep, handles compression at roughly 3.5 times the load capacity of wood. Put it on the belly where compression lives, and the bow's resistance to set increases by the same factor. The sinew still handles tension on the back. The horn and sinew, bound together with hide glue, form a structure where each material does exclusively what it does best. The hide glue deserves a moment of attention because it is not incidental to the design. Hide glue is made by boiling animal skin, hooves, or cartilage, releasing the collagen that holds connective tissue together. Collagen is also what sinew is made of. When sinew fibers are laid in hide glue, the adhesive has molecular-level chemical compatibility with the fibers it binds. The bond isn't surface adhesion. It's more intimate than that. And the glue itself shrinks as it cures, adding incrementally to the sinew's pre-tensioning force. A bow of this construction, completed and cured, was not a product you measured in weeks. The sinew application alone, separating the fibers by hand, mixing with warm glue, applying each layer and waiting for it to set before adding the next, took weeks on its own. A horn composite bow required roughly 3 months from raw materials to finished weapon. The Jackson Hole Historical Society's research on sheep-eater weapons documented that bows of this quality could command up to 10 horses in trade. That was not merely a weapon. That was a significant measure of wealth. The wood question runs parallel to all of this, and it explains something the trappers noticed without being able to fully account for. Some bows from certain regions hit significantly harder than comparable bows from other regions, even when the construction looked similar. The answer was in the stave. Osage orange Maclura pomifera grows, or grew naturally, in a small and specific area, the Red River drainage of northeast Texas, southeast Oklahoma, southwest Arkansas, and adjacent Missouri. French traders called it bois d'arc, wood of the bow, a name direct enough that it needs no translation. The Caddo people of that same Red River country had been harvesting and trading it for centuries before Europeans arrived. Henri Joutel, traveling with La Salle's expedition in 1687, documented that tribes made journeys of 200 miles specifically to trade with the Caddo for bois d'arc bows. The material properties of Osage orange read like a specification written for bow making. Specific gravity of 0.86, about 30% heavier than white oak. A modulus of rupture of 18,650 pounds per square inch. A bow performance index, the ratio of bending strength to elastic modulus, which bowyers call the bow index, of 11.5. That number is essentially identical to European yew, the wood English longbowmen spent centuries cultivating and hoarding. But Osage orange is harder, denser, more resistant to rot, and more available than yew ever was in North America. Meriwether Lewis reported in 1804 that tribes traveled many hundreds of miles in search of Osage orange. John Bradbury documented around 1,810 that a single Osage orange bow could be traded for a horse and a blanket. Museum collections and specialist research have confirmed that Osage orange bows reached the Shawnee and Wyandot in Ohio and the Blackfoot in Montana, distances exceeding 2,000 miles from the tree's original range. Frank Schambach, an Arkansas archaeologist, argued on the basis of excavated evidence that control of the Osage orange trade may have underpinned the wealth of the Spiro Mounds culture in eastern Oklahoma, a Mississippian polity that flourished between 1,250 and 1,450 CE. The Comanche, who were perfectly positioned geographically to access the best Osage orange, made bows from it that apparently needed no sinew backing at all. The wood's compression resistance was high enough that set was not a practical problem. No sinew-backed Comanche bow has been positively identified in museum collections, and specialist bowyer research examining original specimens confirms this pattern. They were already building with the best compression-resistant material available in North America. By the mid-1830s, the mountain men who had been in the Rockies long enough to watch how things actually worked had arrived at a specific and uncomfortable conclusion. The bow they had spent their first seasons dismissing was, in several important tactical categories, a better weapon than their rifles. Josiah Gregg, 8 times across the Santa Fe Trail in the 1830s and 1840s, put the arithmetic plainly in Commerce of the Prairies. While the musketeer loaded and fired once, the bowman discharged a dozen arrows, at distances under 50 yards with accuracy nearly equal to the rifle. That was not partisan enthusiasm for native weapons. That was observation from a man who had watched both in use repeatedly under field conditions. The numbers behind Greg's observation are worth sitting with. George Catlin witnessed Mandan warriors keeping 8 arrows in the air simultaneously. His estimate was 15 to 20 arrows per minute from a capable bowman. Comanche riders on horseback could reportedly approach 30. A skilled rifleman with a flintlock in good conditions managed 2 to 3 aimed shots per minute, and that assumed dry weather, clean priming, no fumbled balls, and the ability to stand reasonably still. The flintlock fired successfully roughly 7 times in 10 under ideal conditions. Rain made the powder wet. Cold thickened the grease on the patch. Snow crept into the pan. The bow worked in rain, in snow, in cold that seized the locks of rifles. It made no sound that carried. It required no supply chain of powder, lead, and flints. Every piece of it could be made from what the land provided. Nathaniel Wyeth complained from the field in 1834 that the trappers' powder was so badly damaged that their flintlocks had become unreliable, and that hunters commonly had miserable flint guns that snapped continually. The Comanche, who fought those same hunters over the same terrain, had no such problem. The tactical asymmetry was real enough that it shaped a generation of fighting on the southern plains. The Comanche strategy of drawing an opponent's fire, waiting through the reload interval, then closing at speed worked because the bow's rate of fire made a single-shot weapon's reload time lethal. That equation held until 1844, when Captain Jack Hayes's Texas Rangers used 5-shot Colt Patterson revolvers at the Battle of Walker's Creek. The first time repeating firearms gave mounted men a rate of fire that could match the bow. That battle, not the invention of the rifle, was what actually broke the tactical dominance of the short composite bow in the American West. The range advantage of the rifle was real and significant, however. A Hawken, the heavy plains rifle that became standard equipment for mountain men, was accurate to 200 yards and beyond by a skilled shooter. A plains bow was effective to roughly 50 yards, most effective inside 30. At distance, in open terrain with a stationary target, the rifle was simply a different kind of weapon operating in a range envelope the bow couldn't reach. Men like Beckworth and Bridger understood both weapons intimately. They didn't argue about which was better in the abstract. They understood that the answer was entirely situational, and they had the practical knowledge to make that call case by case. Paul Kane, the Canadian artist who traveled among plains tribes in the 1840s, wrote of watching a warrior drive an arrow entirely through the body of a buffalo. The arrow, after passing through the animal, stuck in the ground on the far side. George Catlin confirmed that this happened not rarely, but as a documented occurrence. A bison weighs close to 2,000 pounds. The hide on the shoulders is thick enough that a modern hunting arrow loses significant velocity just clearing it. What Kane and Catlin were watching was the delivery of enough kinetic energy from a bow barely long enough to reach a man's shoulder to penetrate through an animal the size of a small car. That performance came directly from the design. The composite bow stores energy more efficiently than a simple wood stave because the pre-tensioned sinew begins contributing to the limb's return force before the bow is even fully drawn. On release, both the wood's spring back and the sinew's powerful contractile pull drive the limbs forward simultaneously. The stored energy in the limb at full draw is higher per unit of bow length than any single material bow can achieve, because the materials are working in their respective zones of maximum efficiency. Edwin Denig, who spent more than 20 years living among Upper Missouri tribes as an American Fur Company trader, documented something that clarified where the weapon's practical value was understood most clearly. Every tribe, he observed, used the bow exclusively for buffalo hunting on horseback, even in the 1850s, when firearms had been available through trade for decades. The Northwest shotgun was for hunting on foot. The bow was for the chase because of rate of fire, silence, reliability on a galloping horse, and the fact that reloading a muzzleloader while riding at full speed into a bison herd was a reliable way to get yourself killed. Francis Parkman, at the Oglala Sioux camps in 1846, watched Raynal, a French-Canadian trader with full access to firearms, deliberately use a native bow for his buffalo hunting. Raynal was not performing cultural deference. He was using the tool that did the job better. Back to Ruxton's 3-foot stick. He held it near the end of the fur trade era, in a period when the mountain men were already dispersing the beaver played out, the fashion for felt hats gone, the rendezvous system collapsing. What Ruxton held was an artifact of a manufacturing tradition he had no framework to evaluate properly. He knew it was powerful. He knew it was old and still powerful. He couldn't explain why. The explanation lives in the sinew. Specifically, in what sinew is doing at a molecular level when it's wrapped around the back of a bow. Sinew is collagen, the same protein that makes up the connective tissue running through every vertebrate body. When it dries, the collagen fibers shorten. When they're oriented lengthwise along a bow limb and bonded there under the influence of hide glue made of the same protein, that shortening is constrained. The fibers can't pull back to their preferred resting length. They stay stretched, slightly, permanently, under a residual tension that pushes the bow limb away from the archer and toward reflex. An English longbow kept strung over winter would follow the string. The bellywood would take a slight permanent compression set, and by spring the bow would have lost 2 or 3 pounds of draw weight and some fraction of its cast. An unstrung sinew-backed bow left in a cool, dry lodge for that same winter would, if anything, emerge with slightly more reflex than it had in the fall. The sinew's contraction continued slowly in the dry air. The bow was, in a mechanical sense that no one in the 1840s had language for, self-correcting. The craftsmen who made these bows didn't know the word collagen. They didn't know what pre-stressed composite structures were. They knew, from long observation and careful transmission of knowledge, that bows built this way lasted, and bows built other ways didn't. They knew what materials to use, and what the finished weapon should feel like when strung. The physics was implicit in the practice. Osborne Russell encountered this knowledge in its most refined form, in the Yellowstone country, among people who owned almost nothing, but understood exactly how to make weapons of extraordinary quality from the materials the land provided. His account of the mountain Shoshone bow has a quality to it, a quality of a man trying to describe something he recognizes as excellent, without quite being able to explain the excellence. The bow was beautiful, yes. The ornamentation with porcupine quills was genuine craft. But what stopped Russell, what made him spend the words he spent, was the physical performance of the thing, 3 feet long, made from mountain sheep horn and sinew and boiled hide glue and patience, worth 10 horses in trade when made well, still performing years after it was made, in a way that contradicted what every English-speaking settler knew about bows and wood and time. The answer to why it never lost its pull is the same answer to a dozen other questions about what European observers got wrong about the cultures they were encountering. The assumption that something made without metal tools, without a written tradition of engineering, without universities or metallurgy, must be simple. That assumption was wrong. The engineering was sophisticated. The materials science was correct. The sinew-backed bow was doing exactly what a pre-stressed composite structure does, for the same reasons, and the fact that the people who built it described that function in different language than a modern materials engineer would use doesn't change what was happening inside the limbs when the string was drawn. George Catlin, who painted the Plains tribes in the 1830s before the epidemic years reshaped everything, spent time in Mandan earth lodges, watching warriors who could keep 8 arrows in the air simultaneously. He was watching men who had spent their entire lives developing a skill with a weapon built by craftsmen who had spent months on each individual bow. The bow and the archer were a system, and each part of that system had been refined over generations through exactly the kind of empirical testing that produces reliable knowledge. If the bow broke, you changed the design. If the sinew delaminated, you changed the glue. If the weapon lost power over seasons, you figured out what was missing. What was missing, in the bows that failed, was the pre-stress, the active, ongoing tension of dried sinew pulling a limb toward reflex and keeping it there against the forces that always, in simpler weapons, won. There's a record that stays close to this whole story, not from a trapper's journal, but from a much later interview with a Comanche elder, recorded by anthropologist Wallace Hobel in the 1930s. The elder was describing how bows were made, and he said, more or less, that the test of a good bow was not how it shot when new, but how it shot after 2 winters. Any bow could be made to shoot when it was fresh. The question was whether it held. The Comanche standard for a bow's quality was longevity of performance, not initial draw weight, not first-day accuracy, but whether the weapon held its character over years of real use. The sinew-backed composite bow held. It held because it was built to hold, because the people who made it understood, without calling it by that name, that the difference between a bow that held and a bow that didn't was a layer of dried collagen fibers pulling continuously in one direction, preloading the structure against the forces that worked against it every time it was drawn. The mountain men who picked up old bows and felt what Ruxton felt, that pull, intact and powerful after years and years of use, were encountering an engineering solution so well matched to its problem that it was essentially invisible. The bow looked simple: 3 feet, a curve, a string. The mechanism that kept it performing was hidden inside the structure, working quietly between shots, between hunts, through the long winters when it sat unstrung against the lodge poles. James Beckwourth shot this bow. Osborne Russell admired it. Josiah Gregg counted its arrows against the musketeers' shots and wrote down what the number told him. And somewhere in the Crow camps, near the Bighorn Mountains, in the Shoshone lodges in the Yellowstone backcountry, in the Comanche rancherias on the Llano Estacado, craftsmen were separating sinew fibers by hand, warming hide glue over small fires, and laying the backing that would still be pulling, still fighting the string, long after those craftsmen were gone.